In this lesson, we're taking those trig identities that we were using in the last lesson, and we're using them to verify a trig identity. So remember in algebra that when we solved an equation, we realized that it was an identity when we saw that both sides of the equation were equal. But we already knew that that was an equation. Here, we're trying to prove that it is a true equation. And so, again, kind of back and forth between algebra and the trig identity use that we're doing now. In algebra, because you knew it was an equation, you were able to add stuff to both sides, subtract stuff from both sides, multiply, divide. Here, since we're trying to prove that the equation is true, we can't use those properties of equations to do so. So what we're basically doing is taking, most of the time, one side of the equation and working with it until you end up with the exact same thing on the other side. In example 1, I look at part A and I notice that the left side seems more involved than the right side, so I'm going to work with the left side. So I have secant squared and cotangent squared. So maybe a good first step might be to break those down into sines and cosines. So I've got 1 over cosine squared of theta times cosine squared of theta over sine squared of theta. And I notice that I can cross cancel these and get 1 over the sine squared of theta. Oops, I missed this minus 1 in this first step. Let me make sure I carry that down. I know that 1 over the sine squared of theta is equivalent to the cosecant squared of theta, now minus 1. And whenever I see cosecant squared or cotangent squared, pretty much any trig function squared, and a plus 1 or a minus 1, I'd like you to realize, hey, maybe I should look at my Pythagorean identities, because there's always something squared and a 1 in there. And so in my Pythagorean identities, I have this one. I'm just going to jot it down off to the side. I have 1 plus the cotangent squared of theta equals the cosecant squared of theta. And so since I know that, I can substitute in this for the cosecant squared. And when I do that, I have 1 plus the cotangent squared of theta minus 1. And then finally, the 1's cancel out, leaving me with cotangent squared of theta, which equals the right side of my equation. I have verified that identity. So that's the kind of thinking that we're using here. We're working one side of the equation and pretty much simplifying it down until we end up with the other side of the equation. So let's use that same thinking in part B. In part B, I look at that identity, and this time the right side of the equation looks more involved. So I'm going to work on that side. So I'm not doing anything to the left-hand side. So tangent squared of alpha, I'm trying to show is equal to that stuff on the right. So that stuff on the right, secant of alpha is equivalent to 1 over the cosine of alpha. Cosecant is equivalent to 1 over the sine of alpha. Tangent, we know, is sine of alpha over cosine of alpha, and then minus 1. Right away, hopefully you see this cross-reducing I can do, and then I simplify, and I have 1 over the cosine of alpha minus 1. Well, that that's cosine squared. of alpha, excuse me. We know that 1 over the cosine is equivalent to secant, so I'm going to rewrite this as secant squared of alpha minus 1. And again, I have a trig function squared with a 1, so let me look at my trig ratios and my Pythagorean identities. And I notice on my reference sheet this thing that I'm going to write off to the side. 1 plus tangent squared of theta equals secant squared of theta. So I can once again take this and substitute it in here. And when I do, I have 1 plus tangent squared of theta minus 1. My 1's cancel out. And I'm left with tangent squared of theta, which equals that left side of the equation that I was trying to bring it to equal to. When we have fractions, we're doing a lot of the same stuff that we did in the last lesson. We're combining fractions and simplifying it down so that hopefully we can get it to look like, in this example, the right-hand side. So that 1 plus sine of theta and 1 minus sine of theta, I'm going to get a common denominator of 1 minus sine of alpha, alpha squared. So I'm going to multiply top and bottom by 1 minus sine of alpha in my first ratio. So 1 minus sine of alpha times the cosine of alpha over 1 minus sine squared plus 1 plus sine of alpha times the cosine of alpha over 1 minus sine squared. Oops, I'm mixing up my Greek letters. I don't want to do that. And I'm going to distribute in those numerators because things are going to cancel out nicely for me. So that's going to be cosine of alpha minus cosine alpha sine alpha plus cosine alpha plus cosine alpha sine of alpha all over, and I'm trying to get this to equal to the right-hand side. Well, I have it over 1 minus sine squared of theta. And remember this Pythagorean identity. Cosine squared of alpha plus sine squared of alpha equals 1. And so I can replace the 1 with sine squared plus cosine squared. So I'll have sine squared of alpha plus cosine squared of alpha, that's the 1 that I've just substituted in for, minus sine squared of alpha. Whew. Well, these are going to conveniently cancel out. And so are these. So now I've got 2 cosine of alpha over cosine squared of alpha. I can reduce those and get 2 over cosine of alpha. And finally, when I use another reciprocal property, I would have 2 secant of alpha, which is what I was trying to show it was equal to. In this example, the instructions say verify by multiplying, and what they mean by that is I'm using kind of the same strategy that I did in the last one. The only difference is that in the last one I was multiplying top and bottom by something so that I could combine my fractions. In this one, once again, anytime you see a trig ratio with a 1 in the denominator, it's probably a good bet to multiply by the conjugate of it so that maybe you can use a Pythagorean identity in order to clean that up a little bit. So I'm going to rewrite this as tangent of secant x plus 1. I'm multiplying by secant x minus 1 in the numerator and denominator. So that in my denominator, I have secant squared of x minus 1, and in my numerator, I have secant x tangent x minus tangent of x. So on my reference sheet, I see that secant squared of x with a 1 in it, and I automatically look at my reference sheet and I notice this guy again, 1 plus tangent squared theta equals secant squared theta. So I'm going to substitute in that 1 plus tangent squared of theta. So I have secant x tangent x minus tangent x all over 1 plus tangent squared of x minus 1. These cancel out, and let's take this fraction and break it up a little bit. So now I'm going to have secant x over tangent x, because I have the tangents reducing, and then minus 1 over the tangent x, again, because they're reducing. Now this tangent x, this 1 over tangent x that I'm looking at here, right away, I see how it's going to become cotangent of x. I'm just going to take the reciprocal of it. So that part is done. So let me go ahead and get that cleaned up. Secant x over tangent x minus cotangent x. All right, now I've got to clean up this secant x over tangent x. So what is this? This is 1 over cosine x over the sine of x over cosine x. Well, when I simplify that fraction, notice that both of the fractions in this complex fraction have this cosine as the denominator. That means those cancel each other out. And I've got 1 over sine of x now minus cotangent x, and I believe I'm home free because look at what, oh my goodness, I've been writing for a while. Look at what I was trying to show. So finally, this is cosecant x minus cotangent. Notice in the instructions that we're going to verify this trig identity by factoring. So you're looking at this identity, and the left-hand side, whew, that's a lot more complicated to look at than the right-hand side. So the instructions say I'm going to be factoring. Well, what can I factor out? What do they have in common? They both have tangent squareds, and they both have cosecant squareds. So I'm going to factor those out and kind of see where things fall from there. So when I factor tangent squared x, cosecant squared x from this expression, I have sine squared x plus cosine squared x. Well, that's magnificently convenient because one of our Pythagorean identities is that sine squared x plus cosine squared x is 1. Okay, so that pretty much just cancels out. So I've got, now I have tangent squared of x cosecant squared of x that I'm trying to verify is equal to secant squared of x. Well, at this point, let's change everything into sines and cosines. Tangent squared is sine squared of x over cosine squared of x. And cosecant squared is 1 over the sine squared of x. And, well, this is convenient. These cancel out. And so I have 1 over the cosine squared of x, which naturally will simplify to secant squared of x, which is what I was trying to show it was equal to. So hopefully you're kind of realizing that this is not a kind of question that lends itself towards multiple choice. Just like back in geometry when you were doing proofs, it was very hard to do a multiple choice kind of proof. So it'll be interesting to see how this gets assessed. Finally, I mentioned earlier that you can't add stuff to both sides or multiply things on both sides. And sometimes you have to kind of work on one side and simplify it down and work on the other side and simplify it down so that you can figure out how you're going to get one side to equal the other. So in the left-hand side, I would notice that I can factor out a secant squared of x. So secant squared of x will become secant squared of x minus 1 inside the parenthesis when I factor that out. Once again, I know that 1 plus tangent squared of x equals secant squared of x. So I can take that and substitute it in inside this parenthesis. So I have secant squared of x times 1 plus tangent squared of x minus 1. These are going to conveniently cancel out, and I'll have secant squared of x times, I don't really know the parentheses, times tangent squared of x. And some of you might already realize that you're going to use this in order to get the left-hand side to equal the right-hand side. Some of you might get to this point and kind of be at an impasse for how am I going to get this left-hand side to equal this. So we pause the left-hand side and we work the right-hand side. So I look at this right side of the equation and I realize I can do the exact same thing that I did on the left-hand side. I can factor out a tangent squared of x in this instance. So when I do that, I have tangent squared of x times tangent squared of x plus 1. Well, oh, that's pretty convenient. Remember this guy? So that means that tangent squared of x times secant squared of x. And notice I've reached the point at which left side equals right side, okay? But I can't stop here. I'm not done until I've taken one side of the equation and made it match the other. The reason why we work both sides separately, however, is if you didn't look at this and already realize that you're going to use this trig identity again in order to kind of translate this secant stuff into tangent stuff, then the process of working the right-hand side out helps us maybe get the idea. If it's not necessary for you to work the right-hand side in order to see that, then save yourself some time, okay? But you can work each side separately so that you see the point at which the two sides of the equation will kind of match up, and what you need to do to one side in order to achieve that. All right, so coming back to this secant squared of x times tangent squared of x. I'm going to erase this underlining so it doesn't look like a fraction. If I'm using this trig identity, I can substitute in for this secant squared x, that 1 plus tangent squared of x. So 1 plus tangent squared of x times tangent squared of x. Distribute that tangent squared of x, and there we have it. Tangent to the 4th of x plus tangent squared of x, which is what I was aiming for.